machine learning, data isn't just important, it's everything. Data acts as both the foundation and the fuel. Without it, our algorithms can learn. So data matters, especially for deep learning. The more data we have, the better these models perform because they can identify patterns more accurately and make better predictions. Deep learning models, in particular, require vast amount of data to function optimally. They thrive on it because the complexity of the tasks they perform, like recognizing images or processing natural language, demands extensive data to capture all the nuances involved. But where does all this data come from? For different applications, researchers rely on a carefully curated dataset that provide the volume, variety, and quality needed to train models effectively. Let's take a closer look at how large datasets shape different areas of deep learning. First, let's take a look at image-based inference. Consider ImageNet, a massive repository of over 14 million images categorized into 1,000 object classes. ImageNet has been instrumental in advancing object recognition technologies, setting the benchmark for deep learning in computer vision. Then there is Microsoft COCO, which stands for Common Objects in Context, which contains more than 300,000 images with 1.5 million object instances across 80 object categories. Unlike ImageNet, COCO emphasizes object detection, segmentation, and scene understanding, making it a go-to dataset for models that need contextual awareness in images. And let's not overlook Google's JFD 300M, a colossal dataset with 300 million images spanning millions of labels across over 18,000 classes. This dataset is crucial for training large-scale vision models, improving pre-training efficiency and generalization performance in real-world applications. These datasets are essential because they provide the variety and volume of data needed for models to learn effectively and generalize their learning to new unseen images. But deep learning isn't just about images. Text-based models also depend on massive datasets to function effectively. Now let's shift our focus to large language models or LLMs. LLMs such as OpenAI's generative pre-trained transformer, which all of you know is called GPT, are trained on diverse and extensive datasets to capture a broad spectrum of human knowledge. These models rely on datasets such as Common Crawl, Books Corpus, OpenWebEx, and Wikipedia. Together, these datasets enable LLMs to perform a wide range of tasks, from answering questions and summarizing text to writing essays and generating human-like dialogues. But what happens when we combine text with images? That's where models like Stable Diffusion come into play. Stable Diffusion, initially released in 2020 by Stability AI, is a multimodal foundation model that generates images from textual description. Stable Diffusion follows two-step training process. First, it learns from millions of low-resolution images to recognize basic visual patterns and concepts. Then, it refines its ability by training on higher resolution images, allowing for the generation of detailed, high-quality artwork and photorealistic images. The training process relies on massive datasets with billion samples such as LAION 2BEN and LAION 5B. These datasets push the boundaries of AI creativity, demonstrating how large-scale training data can enable AI to generate original, highly detailed content. Now, let's transition to small data. So far, we have discussed how deep learning thrives when massive amounts of data are available. But what happens when we don't have enough data? What if collecting data is too expensive, time-consuming, or even impossible due to privacy and security restrictions? This is where small data comes into play. Unlike big data contexts, small data domains are those where gathering or labeling data is prohibitively expensive or constrained by privacy and security laws. For example, in healthcare and medical domain, we often have an abundance of healthy subjects, but very few sick subjects, making it difficult to train models on rare conditions. Individual differences that require personalized training, meaning that a model trained on one group may not generalize well to another. A high cost of obtaining data. Certain medical tests take a lot of time, expertise, and money to collect. If we think about data availability across different types of subjects, we can see an increasing challenges as we move from rat to apes to healthy adult to sick adult to healthy children and finally to sick children, where obtaining sufficient data becomes extremely difficult. But small data is not just about quantity. It is also about quality. If a model is trained on rats, applying that same model to sick children would likely lead to failure. This discrepancy is known as domain gap, where models trained on one distribution fail when applied to another. So how do we address the challenges of small data? This is what the Machine Learning with a Small Data course aims to cover. In machine learning, the lack of data doesn't always mean we can't train models effectively. Instead, we rely on two key strategies. One, data-efficient machine learning, techniques that make better use of limited data, such as transductive or inductive transfer learning. And two, synthetic data augmentation, which means generating additional training samples using physics-based simulation or data-driven generative models to expand our dataset artificially. Throughout this course, we recommend that these two approaches are used together to compensate for the lack of real-world data from the target domain. Of course, the choice of method depends on the specific problem, available resources, and the characteristics of the dataset. Just as big data revolutionized AI, advancements in data-efficient learning and synthetic data generation are unlocking the potential of AI even in scenarios where data is scarce. So, as you move forward, remember, better data leads to a smarter AI, but innovation thrives even when data is small. Through techniques like transfer learning, synthetic data generation, and data-efficient machine learning, we can tackle the challenges of small data and continue advancing AI. Keep learning, keep experimenting, and keep pushing the boundaries of what's possible, because even a small data can make a big impact.